Close your eyes and imagine the most perfectly organized room you have ever seen. Every book stands in its exact place on the shelf. Every pen rests in its designated holder. The bedsheets stretch smooth and tight, without a single wrinkle. The air itself seems to hold its breath, maintaining this beautiful stillness. Now expand this image beyond the room, beyond your house, beyond your city. Picture a world where every grain of sand knows its position on every beach. Where every drop of water in every ocean holds its perfect place. Where every cloud drifts along its predetermined path across the sky. This is what scientists call perfect order. It is a state where everything exists in its most organized form possible. Like a symphony where every note plays at exactly the right moment, creating harmony that never falters. In this perfectly ordered universe, crystals would grow with mathematical precision. Salt crystals would form perfect cubes. Snowflakes would display their six-sided symmetry without variation. Each crystal would be identical to every other crystal of its kind, following nature's blueprint exactly. The stars themselves would align in perfect patterns across the night sky. Galaxies would spin in synchronized harmony. Planets would orbit their suns in flawless circles, never deviating from their assigned paths. The entire cosmos would move like the most intricate clockwork ever imagined. But here is where the story becomes interesting. This perfect order, as beautiful as it sounds, carries within it a deep restlessness. Even in a universe of complete organization, something fundamental stirs beneath the surface. Think about a deck of cards, fresh from its package. Every card sits in perfect sequence. Ace through king, hearts, diamonds, clubs, spades. The order is complete and predictable. Yet the moment you pick up this perfect deck, something changes. The oils from your fingers, the slight pressure of your touch, the microscopic movements of air around your hands, all begin to introduce tiny variations. This is the first whisper of what scientists call entropy. It is not destruction or chaos, but rather the universe's natural tendency toward change. Like a gentle current beneath still water, entropy flows through all things, encouraging them to explore new arrangements. In your perfectly ordered room, entropy begins its work immediately. Dust particles settle on surfaces that were just cleaned. Air molecules mix and move, carrying scents from one corner to another. The sunlight streaming through your window gradually fades the colors of objects it touches. These changes happen so slowly, so gently, that you might not notice them at first. Your body itself demonstrates this beautiful tension between order and change. Right now, as you rest, millions of cells work together in remarkable coordination. Your heart beats in steady rhythm. Your lungs expand and contract with perfect timing. Your blood carries oxygen to exactly where it needs to go. This is biological order at its finest. Yet even as your body maintains this incredible organization, change flows through every part of you. Old cells die and new ones take their place. The food you ate earlier transforms into energy. Your memories reorganize themselves as you prepare for sleep. You are both perfectly ordered and constantly changing, all at the same time. This is the paradox that has fascinated scientists for centuries. How can something be both organized and changing? How can order and disorder exist together? The answer lies in understanding that the universe is not static, like a photograph frozen in time. Instead, it is dynamic, like a river that maintains its shape while its water constantly flows. In a world of perfect order, every process would eventually stop. There would be no energy left to power change. No heat would flow from warm places to cool places, because everything would already be the same temperature. No chemical reactions would occur, because all materials would already be in their most stable forms. Time itself might seem to stand still. But our universe is not perfectly ordered. It pulses with life and change and movement. Stars are born in clouds of cosmic dust, burn brilliantly for billions of years, then transform into new forms of matter and energy. Planets cool and warm through geological ages. Life emerges, evolves, and creates new kinds of complexity. This ongoing transformation is not random chaos. It follows patterns and laws that scientists have been discovering for hundreds of years. These laws describe how energy moves, how matter changes, and how time flows forward. They reveal that our universe is like a vast, slow dance between order and change. As you lie here tonight, you are part of this cosmic dance. Your breath mingles with the air around you. Your body heat gradually warms your blankets. Your thoughts settle into the quiet rhythms that prepare your mind for sleep. You are experiencing entropy in its gentlest form, as your body transitions from the organized activity of waking into the different kind of order that comes with rest. The perfectly ordered universe exists only in our imagination. The real universe is far more interesting. It is a place where order and change dance together, creating the conditions that allow stars to shine, planets to form, and life to flourish. Tomorrow, when you wake, your room will be slightly different than it was tonight. Dust will have settled in new places. Light will have shifted across your walls. Your dreams will have reorganized your thoughts in subtle ways. These changes are not signs of failure or decay. They are signs that you live in a universe alive with possibility. And in this universe of gentle change, something remarkable happens. Simple things combine to create complex beauty. Atoms join to form molecules. Molecules arrange themselves into crystals and cells. Cells work together to create living beings capable of wonder and thought. But how does this happen? How do the simple movements of invisible particles create the intricate patterns we see all around us? Picture your morning cup of coffee, sitting quietly on the table beside you. The dark liquid appears perfectly still, like a small mirror reflecting the light from your window. But if you could see with different eyes that could perceive the invisible world of molecules, you would witness the most extraordinary dance. Billions upon billions of water molecules move within that seemingly calm coffee. They jiggle and vibrate and spin in patterns too small for your eyes to detect. Each molecule is like a tiny dancer, never stopping, never resting, always in motion. This movement has continued since the moment the universe began, and it will continue long after the stars have burned out. The steam rising from your coffee tells this story in visible form. Each wisp of vapor carries water molecules that have broken free from the liquid below. They have gained enough energy to escape the gentle pull of their neighbors and float upward into the cooler air above. Watch that steam curl and twist as it rises. Notice how it spreads and disperses, becoming thinner and more scattered until it disappears from sight. This simple act of spreading is one of the most fundamental processes in all of nature. Scientists call it diffusion, but you can think of it as the universe's way of sharing. When molecules are crowded together in one place, they naturally spread out to fill the available space. Like people leaving a crowded room and scattering into a large hall, molecules move from areas where they are packed tightly to areas where they have more room to move freely. This spreading happens everywhere around you, all the time. The scent of flowers in your garden drifts on the breeze because fragrance molecules leave the petals and disperse through the air. The salt you sprinkle on your food dissolves and spreads evenly throughout the dish. The warmth from a fire radiates outward, carrying heat energy to everything nearby. Each of these processes follows the same gentle law. Energy and matter flow from concentrated places to spread out places. From organized arrangements to more scattered ones. From patterns of order toward patterns of greater freedom. Think about a drop of food coloring falling into a glass of clear water. At first, the color stays concentrated in one small area, creating a bright, intense spot of blue or red. But slowly, the colored molecules begin to move. They bump into water molecules, which bump into other water molecules, setting up a chain of gentle collisions that spreads the color throughout the glass. This process happens without any outside force pushing it along. No hand stirs the water. No pump circulates the liquid. The molecules simply move because movement is their natural state. They carry the color with them as they dance their microscopic dance, until the entire glass becomes evenly tinted. The same principle governs the air you breathe. Right now, oxygen molecules from your last breath are mixing with the air around you. Some of these molecules may travel across the room, out the window, and eventually circle the globe. The oxygen that enters your lungs tonight might have been part of a tree leaf yesterday, or dissolved in ocean water, or drifting through clouds high above the mountains. This constant mixing and sharing creates the conditions that sustain life on Earth. Plants release oxygen that animals breathe. Animals exhale carbon dioxide that plants use to grow. Ocean currents carry nutrients from one part of the sea to another. Weather systems distribute heat and moisture around the planet. All of these processes depend on the fundamental tendency of molecules to spread and share. Your own body participates in this molecular dance every moment of your life. The food you eat gets broken down into smaller molecules that spread through your bloodstream. Nutrients flow from your digestive system to every cell in your body. Waste products move from your cells back to your blood, then to your kidneys and lungs, where they leave your body and join the larger cycles of nature. Even your thoughts depend on molecular motion. The neurons in your brain communicate by releasing tiny amounts of chemical messengers called neurotransmitters. These molecules travel across microscopic gaps between brain cells, carrying signals that create your perceptions, memories, and dreams. As you prepare for sleep tonight, your brain is already beginning to change the types of molecules it releases. Chemicals that promote alertness gradually decrease, while others that encourage rest and restoration increase. This shift happens naturally, following the same principles of molecular movement that govern your coffee cup and the spreading of perfume through air. The ancient Greeks imagined that all matter was made of tiny, indivisible particles they called atoms. They pictured these atoms as solid, unchanging pieces that fit together like building blocks to create everything in the world. But the real story is far more beautiful and dynamic. Atoms are not solid building blocks but clouds of energy and possibility. They join together to form molecules, and these molecules never stop moving. They vibrate, rotate, and travel through space in patterns that create the textures and experiences of your daily life. The warmth you feel when you hold your coffee cup comes from fast-moving molecules bumping against your skin. The smoothness of the ceramic surface results from molecules arranged in orderly patterns. The liquid nature of the coffee itself emerges from molecules that slide past each other while remaining loosely connected. Temperature is simply a measure of how fast molecules move. In ice, water molecules vibrate slowly while locked in rigid positions. In liquid water, they move faster and can slip around each other. In steam, they move so quickly that they break free entirely and fly through the air as individual molecules or small clusters. This connection between molecular motion and temperature reveals something profound about the nature of heat itself. Heat is not a substance that flows from one object to another. Instead, it is the energy of molecular movement, spreading from places where molecules move quickly to places where they move more slowly. When you wrap your hands around a warm mug, fast-moving molecules in the ceramic transfer some of their motion to the slower-moving molecules in your skin. This energy transfer continues until the molecules in both your hands and the mug are moving at similar speeds. At that point, they feel the same temperature to your touch. This process of energy sharing drives much of what happens in the world around you. It explains why ice melts in warm air, why hot soup eventually cools to room temperature, and why the sun's energy can warm the entire Earth despite the vast distance between our planet and its star. But there is something mysterious about this process of spreading and sharing. Once molecules have spread out evenly, once energy has distributed itself uniformly, why doesn't everything simply reverse itself? Why don't the scattered coffee molecules suddenly gather back together? Why doesn't spilled milk spontaneously spill itself? The answer to this question touches on one of the deepest mysteries of time and existence itself. Tonight, as you rest beneath your blankets, heat is making a gentle journey from your body into the world around you. This journey follows an ancient pattern, as predictable as water flowing downhill, as certain as night following day. Heat always travels from warmer places to cooler places, never the reverse, carrying with it one of the universe's most fundamental truths. Feel the warmth radiating from your skin into the cooler air of your room. This heat began its journey deep within your cells, where tiny molecular furnaces called mitochondria burn the fuel from your last meal. These microscopic power plants work tirelessly, converting sugar and oxygen into the energy that keeps your heart beating, your lungs breathing, your thoughts flowing. But not all of this energy becomes useful work. Much of it transforms into heat, like the warmth you feel from a car engine or a computer that has been running for hours. This heat spreads through your tissues, carried by your bloodstream to every corner of your body. Your skin becomes a gentle radiator, releasing this warmth into the surrounding air. The air molecules near your body absorb this heat energy and begin moving faster. As they speed up, they bump into neighboring air molecules, passing along some of their energy. These molecules, in turn, collide with others, creating an invisible wave of energy that spreads outward from your body like ripples on a still pond. This process continues until the heat reaches the walls of your room, where it transfers into the wood, plaster, or brick. From there, it travels through the building materials and eventually reaches the outdoor air, where it joins the vast circulation of heat energy that flows around our planet. Heat moves through the world in three distinct ways, each as natural and inevitable as breathing. The first way is called conduction, and you experience it whenever you touch something warm or cold. When you place your hand on a sun-warmed rock, heat travels directly from the stone into your skin through the contact between your molecules and the rock's molecules. Think of conduction like a line of people passing buckets of water to fight a fire. Each person represents a molecule, and the water represents heat energy. The person closest to the well fills their bucket and passes it to the next person, who passes it along to the next, and so on. The water moves from person to person without any individual person having to run to deliver it. In your body right now, conduction carries heat from your warm core to your cooler skin. The molecules in your muscles and organs pass their energy to neighboring molecules, which pass it to their neighbors, creating a steady flow of warmth toward the surface of your body. The second way heat travels is through convection, which you can observe in the steam rising from your evening tea. As air near the hot liquid warms up, it becomes less dense and rises, carrying heat energy upward. Cooler air flows in to take its place, creating a gentle circulation pattern that distributes heat throughout the room. Your own body uses convection to regulate temperature. Blood warmed by your internal organs flows through vessels near your skin, where it releases heat into the surrounding air. The cooled blood then returns to your core to be warmed again, creating a circulation system that works like the heating system in your home. Ocean currents follow the same principle on a vast scale. Warm water near the equator rises and flows toward the poles, while cooler water sinks and flows back toward the equator. This global circulation helps distribute the sun's heat around the entire planet, moderating temperatures and creating the weather patterns that sustain life. The third way heat travels is through radiation, perhaps the most mysterious and beautiful of all. Unlike conduction and convection, radiation does not require any material to carry it. Heat can travel as invisible waves of energy through empty space, just as light travels from the sun to Earth across the vacuum between them. Every object with temperature above absolute zero radiates heat energy into space. Your body radiates heat right now, though you cannot see these waves with your eyes. Special cameras that detect heat radiation would show you glowing like a gentle flame in the darkness, your warmth painting patterns of light invisible to ordinary vision. The sun's heat reaches Earth entirely through radiation, traveling 93 million miles through the emptiness of space to warm your planet. This radiant energy drives the water cycle, creates weather, powers photosynthesis in plants, and ultimately provides the energy for almost all life on Earth. But here is what makes heat's journey so profound and mysterious. While heat can travel in all these different ways, it always moves in the same direction. Heat flows from hot objects to cold objects, never the reverse. A hot cup of coffee always cools down to match the temperature of the room around it. The coffee never spontaneously becomes hotter by drawing heat from the cooler air. This one-way flow of heat creates what scientists call the arrow of time. It is one of the few physical processes that clearly distinguishes past from future. If you watched a movie of ice melting in warm air, you could easily tell whether the film was playing forward or backward. Ice always melts in warm air, and liquid water never spontaneously freezes in warm temperatures. This directionality of heat flow connects to something deeper about the nature of energy itself. When heat spreads from a concentrated source, like your warm body, into a larger, cooler environment, the energy becomes more scattered and dispersed. It does not disappear, but it becomes less organized, less able to do useful work. Think about a fireplace on a cold winter evening. The concentrated chemical energy in the wood transforms into heat and light as the fire burns. This heat warms your living room, making it comfortable for you and your family. But eventually, all that heat energy spreads throughout your house, then into the outdoor air, then into the vast atmosphere of Earth. The energy has not been destroyed. Every bit of heat released by the fire still exists somewhere in the universe. But it has become so scattered and diluted that it can no longer warm your living room or do any other useful work. It has become part of the background heat energy that fills all of space. This scattering of energy happens everywhere, all the time. Your car engine converts gasoline into motion, but much of the energy ends up as waste heat that radiates into the atmosphere. Your computer transforms electrical energy into computation, but also generates heat that must be carried away by cooling fans. Even your own body converts food into movement and thought, while releasing excess energy as the gentle warmth that now flows from your skin into the night air. Each of these processes follows the same pattern. Concentrated, organized energy transforms into scattered, disorganized heat. This transformation can power useful work, but it always results in energy spreading into forms that become increasingly difficult to recapture and use again. The implications of this one-way flow extend far beyond the simple warming and cooling of objects. It affects the behavior of gases and liquids, the formation of crystals and clouds, the circulation of blood in your body, and the nuclear reactions that power the stars. Heat's patient journey reveals something profound about the architecture of reality itself. The universe seems to have a built-in preference for spreading energy around rather than concentrating it. This preference shapes everything from the formation of galaxies to the beating of your heart. As your body heat continues its gentle migration into the cooler air around you, you are participating in this cosmic process of energy distribution. Your warmth joins the great circulation of heat that flows through our planet and out into space, connecting you to the larger patterns that govern the behavior of matter and energy throughout the universe. But this raises a fascinating question. If energy always spreads from concentrated sources into scattered forms, how did concentrated sources of energy arise in the first place? How did the universe create the stars, planets, and living beings that generate the organized energy we see today? Imagine the universe as a vast balloon, slowly inflating in the darkness of eternity. But this is no ordinary balloon filled with air. Instead, it contains all of space itself, stretching and expanding, carrying galaxies and stars along with it like sparkles painted on its surface. This expansion has been happening for nearly 14 billion years, and it continues right now, even as you rest quietly in your bed. The story begins in a moment so small that no clock could measure it, so brief that light itself could not cross the tiniest distance imaginable. In that first instant, all the matter and energy that would eventually become stars, planets, and you were compressed into a point smaller than the period at the end of this sentence. Then expansion began. Not an explosion into empty space, but the creation of space itself. The universe did not expand into something else. Rather, space grew from within, like a seed sprouting into a plant, but on a scale beyond all imagination. In the first second of existence, the universe grew from subatomic size to larger than a grapefruit. In the next moments, it became larger than our solar system. As space expanded, it carried with it the fundamental forces and particles that would shape everything to come. But here is what makes this expansion so remarkable for our story of heat and energy. As the universe grew larger, it also grew cooler. The energy that had been compressed into that initial tiny point spread out across an ever-increasing volume of space. Think of a drop of ink spreading through a glass of water. As the ink disperses, its color becomes lighter and more diluted. In the same way, as the universe expanded, its energy became more spread out, more diluted. The temperature that had been unimaginably hot in those first moments gradually cooled as space itself provided more room for that energy to occupy. This cooling allowed the first particles to form. In the beginning, the universe was too hot for anything stable to exist. Energy and matter danced together in forms that would instantly transform from one type to another. But as expansion continued and temperatures dropped, protons and neutrons could finally come together to form the nuclei of the first atoms. For nearly 400,000 years, the universe remained too hot for complete atoms to exist. Electrons zipped around freely, unable to settle into stable orbits around atomic nuclei. The universe glowed with intense light, but this light could not travel far before being absorbed and re-emitted by the sea of free electrons that filled all space. Then, as expansion continued its patient work of cooling, something magical happened. The temperature dropped just enough for electrons to join with atomic nuclei, forming the first complete atoms of hydrogen and helium. Suddenly, light could travel freely through space. The universe became transparent for the first time, and the cosmic background radiation that telescopes can still detect today began its journey across the expanding cosmos. This ancient light surrounds you right now. It fills every cubic inch of space in your room, though it has been stretched by billions of years of expansion until it exists as faint microwaves that your eyes cannot see. This radiation is the afterglow of the universe's birth, cooled by expansion from brilliant light to invisible whispers of energy that pervade all of space. But the story of expansion creates a beautiful paradox. If the universe naturally spreads energy into more and more diluted forms, how did stars and galaxies form? How did the smooth, cooling gas of the early universe give rise to the concentrated points of light that shine in tonight's sky? The answer lies in tiny imperfections in the otherwise uniform cosmos. Like gentle ripples on a still pond, small variations in density existed in the early universe. In some regions, matter was slightly more concentrated than in others. These small differences became the seeds of everything we see today. Gravity, that most patient of all forces, began to pull matter toward these slightly denser regions. Over millions of years, gas clouds grew larger and denser, drawing in more material from their surroundings. As these clouds collapsed under their own gravitational pull, they heated up, concentrating energy that had been spread throughout vast regions of space. Eventually, some of these collapsing clouds became so hot and dense that nuclear fusion began in their cores. Hydrogen atoms smashed together with such force that they fused into helium, releasing tremendous amounts of energy in the process. The first stars ignited, becoming brilliant beacons that pushed back against the cosmic expansion with their concentrated light and heat. Stars are remarkable engines of energy concentration. They gather the dispersed matter of interstellar space and compress it until nuclear reactions can occur. Each star burns for millions or billions of years, converting the mass of hydrogen into energy according to Einstein's famous equation. This energy streams outward as light and heat, carrying concentrated stellar energy across the expanding universe. Your own sun follows this ancient pattern. Deep in its core, four hydrogen nuclei fuse together to create one helium nucleus, but the helium weighs slightly less than the original hydrogen. That missing mass transforms into pure energy, following the cosmic speed limit set by the velocity of light. This energy gradually works its way outward through the sun's interior, eventually reaching the surface and streaming into space as the sunlight that warms your planet. The expansion of the universe continues, but now it carries with it these brilliant points of concentrated energy. Stars shine against the darkness, creating islands of heat and light in the growing ocean of space. Planets form from the debris of stellar formation, some of them positioned at just the right distance from their stars to maintain temperatures that allow liquid water to exist. On at least one of these planets, complex chemistry begins to organize itself into patterns that can grow, reproduce, and respond to their environment. Life emerges, representing perhaps the most remarkable concentration of energy and information in the known universe. Living beings like you gather energy from their surroundings and use it to maintain highly organized structures and behaviors. Yet even as stars shine and life flourishes, the expansion continues. Space grows larger, carrying the galaxies away from each other at ever-increasing speeds. The universe becomes more spread out, more diluted, cooler on average than it was in the past. The concentrated energy sources that power stars and life exist like temporary eddies in a river that flows toward greater dispersion. Astronomers have discovered that this expansion is actually accelerating. Some mysterious form of energy, which they call dark energy, seems to be pushing space itself to expand faster and faster. This means that the universe is not only growing larger, but the rate at which it grows is increasing over time. In the far future, billions of years from now, this acceleration will carry distant galaxies so far away that their light will no longer be able to reach us. The night sky will grow darker as the observable universe shrinks, even while the actual universe continues to expand without limit. But tonight, as you rest under a sky still filled with stars, you are witnessing a remarkable moment in cosmic history. The universe has expanded and cooled enough to allow stable atoms, molecules, and complex structures to exist. Yet it remains young enough that stars still shine and planets still orbit in the zones where life can flourish. You are made of elements forged in the nuclear furnaces of ancient stars, organized into patterns of complexity that emerged from billions of years of cosmic evolution. Your very existence represents a temporary victory of organization over the universal tendency toward dispersion. Yet even in your organized complexity, you participate in the gentle flow toward equilibrium. As you prepare for sleep, your body's energy gradually disperses into the surrounding air, joining the patient journey of heat from concentrated sources toward the vast, cool emptiness between the stars. In this cosmic rhythm of expansion and cooling, something profound emerges about the nature of time itself. Hold an ice cube in your palm and watch one of the universe's most profound lessons unfold before your eyes. The solid crystal, with its water molecules locked in perfect geometric patterns, begins to surrender its rigid structure to the warmth of your skin. Drop by drop, the organized ice transforms into liquid water, and this simple change reveals the deepest secret about why time moves in only one direction. In your freezer, water molecules arrange themselves in beautiful hexagonal crystals. Each molecule knows its place, held in position by the gentle attraction of its neighbors. The structure is orderly, predictable, stable. If you could see the molecular architecture of ice, you would witness one of nature's most elegant geometric forms, repeated billions upon billions of times throughout each crystal. This crystalline order represents what scientists call a low entropy state. Entropy is nature's measure of disorder, of how many different ways the parts of a system can be arranged. In ice, the water molecules have relatively few arrangement options. They must follow the strict rules of crystal formation, locking into specific positions that create the solid stable structure. But as your warm hand transfers heat to the ice cube, everything begins to change. The added energy causes the water molecules to vibrate more vigorously. They push against the bonds that hold them in their crystalline positions. Some molecules break free from their neighbors, creating tiny pockets of disorder within the ordered structure. As more heat flows from your hand into the ice, more molecules escape their fixed positions. The rigid crystal lattice begins to collapse in places, creating regions where molecules can move more freely. These molecules slide past each other, tumble over one another, and explore countless new arrangements that were impossible in the solid state. This transformation from ice to liquid water represents a journey from lower entropy to higher entropy. The liquid water has many more possible arrangements than the solid ice. Each molecule can move to countless different positions, creating an almost infinite number of ways for the water to organize itself. The system has become more disordered, more random, more free. Now here comes the remarkable part. Once the ice has melted in your palm, it will never spontaneously freeze back into its original crystalline form, even if you wait forever. The liquid water will not suddenly reorganize itself into the precise geometric patterns of ice, despite the fact that such reorganization would not violate any fundamental laws of physics. Each water molecule in your palm still obeys exactly the same physical laws it followed when it was part of the ice crystal. The forces between molecules remain unchanged. The conservation of energy still applies. Yet the melted water will never return to its original organized state without outside intervention. This irreversibility reveals something profound about the nature of time itself. While the basic laws of physics work equally well whether time moves forward or backward, the statistical behavior of large numbers of particles creates a clear arrow that points toward the future. Time's direction emerges from the tendency of systems to evolve from states with fewer possible arrangements to states with more possible arrangements. Think about a deck of cards fresh from its package. The cards sit in perfect order, ace through king in each suit, arranged in a specific sequence. This represents a low entropy state because there is only one way to arrange the deck to achieve this perfect order. But shuffle the deck once, and the cards assume one of the countless possible random arrangements. The deck has moved from low entropy to higher entropy. Now imagine trying to unshuffle the deck by shuffling it again. You might shuffle for years, decades, centuries, and never accidentally recreate the original factory order. Not because the laws of physics prevent it, but because there are so many more random arrangements than ordered ones. The probability of accidentally finding the one ordered arrangement among the billions of possible random arrangements approaches zero. The melting ice cube follows the same principle. There are countless ways for water molecules to arrange themselves in the liquid state, but only very specific arrangements create the organized crystal structure of ice. When heat gives the molecules freedom to explore new arrangements, they naturally drift toward the more numerous disordered states, simply because there are so many more of them available. This statistical drift toward disorder happens everywhere in nature. A sandcastle on the beach gradually crumbles as wind and waves disturb its organized structure. The organized sand grains scatter in countless different directions, exploring the vast number of random arrangements available to them. The scattered sand never spontaneously rebuilds itself into a castle, despite the fact that such rebuilding would not violate any fundamental physical laws. In your own body, this same principle governs countless processes. The food you eat gets broken down from its organized molecular structures into simpler components that your cells can use for energy. Your breath carries away carbon dioxide, the disordered end product of cellular metabolism. Your body heat radiates into the surrounding air, spreading organized energy into the more random thermal motion of atmospheric molecules. Yet your body also demonstrates something remarkable about entropy and life. While the universe as a whole tends toward greater disorder, living systems can create local regions of increased organization. Your cells take in simple molecules and organize them into complex proteins. Your body maintains its temperature, fights off infections, and repairs damaged tissues. Life temporarily reverses the flow toward disorder, creating islands of increasing complexity in entropy's ocean. But this local decrease in entropy comes at a cost. Your body can only maintain its organization by consuming energy from outside sources and releasing waste heat into the environment. The total entropy of the universe still increases when you include the energy transformations required to sustain life. You create order within yourself by contributing to greater disorder in your surroundings. This balance between local order and global disorder plays out on every scale in nature. Stars concentrate gravitational energy and transform it into the organized nuclear reactions that power their brilliant light. But they also release enormous amounts of heat radiation into the cold emptiness of space, contributing to the universe's overall journey toward thermal equilibrium. Planets form from the gravitational collapse of dust and gas, creating organized spheres of matter. But this organization comes from the release of gravitational potential energy as heat, which radiates away into space. The planet becomes more ordered while the universe as a whole becomes more disordered. Even the formation of galaxies, solar systems, and the complex chemistry that leads to life follows this pattern. Local increases in organization are always accompanied by greater increases in disorder elsewhere. The universe permits temporary victories of order over chaos, but only at the price of accelerating the overall journey toward maximum entropy. This understanding transforms how we think about time's passage. The reason you remember the past but not the future, the reason cause precedes effect, the reason ice melts in your warm hand but never spontaneously freezes, all stem from the same fundamental principle. The universe evolves from states with fewer possible arrangements toward states with more possible arrangements. Time's arrow points in the direction of increasing entropy, toward greater freedom for particles to explore new arrangements, toward the statistical equilibrium where all possible states become equally likely. This direction gives time its meaning and creates the framework within which change, growth, and life become possible. As the last of the ice melts in your palm, you hold not just liquid water, but evidence of time's deepest nature. The transformation you have witnessed connects your small human experience to the cosmic processes that govern the behavior of everything from subatomic particles to the largest structures in the universe. The water in your hand carries within its molecular motion the same principles that drive the expansion of space, the cooling of stars, and the evolution of complexity throughout the cosmos. In this simple melting, you have observed the gentle, inexorable flow that carries all things toward new arrangements, new possibilities, new forms of being. But if entropy always increases, if the universe always moves toward greater disorder, how does light itself behave in this cosmic dance of organization and dispersion? Light a candle in your darkened room and watch as billions of tiny messengers begin their journey into the darkness. Each flame of light represents one of nature's most elegant demonstrations of how organized energy transforms into scattered possibility. The photons streaming from the candle's flame carry with them a story that connects the smallest quantum events to the grandest cosmic processes. Within the candle's flame, molecules of wax vapor dance with oxygen in a controlled chemical fire. This burning releases energy that has been stored in the wax's molecular bonds, energy that originally came from ancient sunlight captured by plants millions of years ago. As the chemical bonds break and reform, they release this stored energy in the form of heat and light. The light emerges as photons, particles of pure energy that have no mass, no electric charge, no substance except their ability to carry energy and information through space. Each photon is born in a specific location within the flame, created by the precise interaction between electrons and atomic nuclei as the burning process releases energy. In the moment of its creation, each photon carries a concentrated packet of energy. This energy is highly organized, focused into a specific wavelength that determines the photon's color and properties. The photon knows exactly where it came from and carries within its wave-like structure the signature of the specific atomic process that created it. But the moment the photon leaves its birthplace in the flame, it begins a journey of dispersion that mirrors the fundamental tendency of all energy to spread from concentrated sources into scattered forms. The photon travels outward in a straight line, carrying its organized energy away from the flame and into the vast space of your room. Some photons travel only a short distance before encountering the surfaces around them. They strike the walls, the furniture, the ceiling, your skin. When a photon hits a surface, something remarkable happens. The organized energy of the photon transfers to the atoms in that surface, causing electrons to vibrate and dance in response to the light's electric field. But these atoms cannot hold onto the photon's energy in its original organized form. Instead, they absorb the photon's energy and then re-emit it in new directions. Some of the energy becomes heat, causing the surface to warm slightly. Some becomes new photons that bounce away in random directions, carrying pieces of the original energy to new locations throughout the room. This scattering of light creates the gentle illumination that allows you to see your surroundings. The photons that left the candle flame in organized streams become scattered throughout your room, bouncing from surface to surface, filling every corner with dispersed light energy. The concentrated brightness of the flame spreads into the gentle glow that surrounds you. Each surface that receives light becomes a secondary source of illumination. Your white walls absorb photons and re-emit them in all directions, creating a soft, even light that reaches into shadowed areas. Dark surfaces absorb more photons and convert their energy into heat rather than scattered light. This is why a black object feels warmer in sunlight than a white object of the same size. The scattering of light follows the same principles that govern all energy dispersion in the universe. Light always flows from brighter regions to darker regions, from areas of high photon concentration to areas of low photon concentration. A candle flame, with its intense concentration of photons, naturally illuminates the surrounding darkness by spreading its light energy throughout the available space. This spreading continues until the photons either escape your room entirely or are absorbed and converted to other forms of energy. The light that reaches your windows travels out into the night, joining the countless photons from street lights, house lights, and starlight that fill the atmosphere. The light that strikes opaque surfaces transforms into gentle heat that warms your room and eventually radiates away into the cooler night air. Your eyes participate in this cosmic process of light scattering and absorption. When photons that have bounced around your room finally enter your eyes, they strike the retina, where specialized cells absorb their energy and convert it into electrical signals. These signals travel to your brain, where they create the visual perception that allows you to see the candle flame and its gentle illumination of your surroundings. But light carries more than just energy. It also carries information about its journey through space and time. The color of light tells you about the temperature and chemical composition of its source. The way light scatters and reflects reveals the textures and properties of the surfaces it encounters. The patterns of light and shadow create the visual information that your brain interprets as the three-dimensional world around you. This information-carrying capacity of light connects your small room to the vast universe beyond. The same principles that govern the scattering of candlelight in your room also govern the light from distant stars and galaxies. Astronomers study starlight that has traveled for millions or billions of years across space, carrying information about stellar temperatures, chemical compositions, and cosmic distances. The light from our sun demonstrates this same process of organized energy becoming scattered. Deep in the sun's core, nuclear fusion creates photons with tremendous energy, concentrated in the form of gamma rays. But these photons cannot travel directly from the core to the surface. Instead, they begin a long journey of scattering that takes thousands of years to complete. Each photon bounces from atom to atom within the sun's dense interior, being absorbed and re-emitted countless times. With each interaction, the photon's energy becomes slightly more dispersed. The high-energy gamma rays gradually transform into lower-energy photons of visible light and infrared radiation. By the time they finally escape the sun's surface, these photons carry the same energy that began in the core, but in a much more scattered and dispersed form. When sunlight reaches Earth, it continues this process of scattering. Our atmosphere spreads the sun's concentrated light into the diffuse illumination that brightens our days. Blue light scatters more than red light, creating the blue color of the sky and the reddish hues of sunrise and sunset. Clouds scatter sunlight in all directions, creating the soft, even lighting that photographers prize on overcast days. Plants capture some of this scattered sunlight and concentrate it back into organized chemical energy through photosynthesis. The green leaves around you are molecular machines that reverse the flow of energy dispersion, at least temporarily, by organizing scattered solar photons into the chemical bonds that store energy for later use. But even this temporary concentration of light energy into chemical form ultimately serves the larger pattern of energy dispersion. When plants die and decay, or when they burn in fires like your candle flame, the stored chemical energy returns to scattered forms of heat and light, continuing the cosmic journey from organization to dispersion. This interplay between concentration and scattering creates the dynamic patterns that make life and complexity possible. Stars concentrate gravitational energy into nuclear fusion, creating intense sources of organized light. Planets and atmospheres scatter this light into the gentler forms that can power photosynthesis and warm the surfaces where life can flourish. Your candle flame represents a small but perfect example of this cosmic process. The organized chemical energy stored in the wax becomes concentrated light and heat in the flame, then scatters throughout your room as dispersed photons and thermal energy. The bright point of the flame creates the gentle illumination that surrounds you, transforming concentrated energy into the scattered glow that lights your evening. As you watch the candle flame flicker and dance, you are witnessing the same fundamental process that governs the behavior of energy throughout the universe. The scattering of light from your candle connects your quiet room to the nuclear furnaces of stars, the vast expanses of interstellar space, and the intricate processes that sustain life on Earth. Yet even as light scatters and energy disperses, something remarkable emerges from this apparent chaos. Complex patterns, living systems, and conscious awareness somehow arise from the interactions of countless scattered photons and dispersed energy flows. As you rest quietly tonight, your body performs the most remarkable act of defiance against the universe's tendency toward disorder. While entropy gently encourages all things to scatter and disperse, your living cells work tirelessly to maintain patterns of extraordinary complexity and organization. You are a temporary victory of order over chaos, a brief arrangement of matter and energy that somehow learned to sustain itself against the flowing tide of cosmic dissolution. Within each of your trillions of cells, molecules dance in choreographed precision that surpasses the most intricate ballet. Proteins fold themselves into exact three-dimensional shapes, creating molecular machines that copy genetic information, manufacture cellular components, and repair damaged structures. DNA strands unwind and rewind with perfect timing, preserving and transmitting the instructions that maintain your body's organization across time. These cellular processes require enormous amounts of energy to sustain their organized complexity. Your mitochondria, the tiny power plants within each cell, burn glucose and oxygen in controlled fires that release the energy needed to maintain life's intricate patterns. This energy flows through carefully managed chemical pathways, powering the countless reactions that keep your biological systems functioning in harmonious coordination. But here lies the beautiful paradox of living systems. While you create and maintain extraordinary order within your body, you can only do so by consuming organized energy from your environment and releasing disorganized energy back into the world around you. Life does not violate the universe's tendency toward increasing entropy. Instead, it borrows organization from one place to create even greater organization elsewhere, while ensuring that the total disorder in the universe continues to increase. Think of your body as a skilled gardener tending a plot of land. The gardener can create beautiful, organized patterns of flowers and vegetables, but only by drawing nutrients from the soil, water from underground sources, and energy from sunlight. The garden becomes more organized and complex, but this local increase in order comes at the cost of greater disorder elsewhere in the ecosystem. Your digestive system demonstrates this principle beautifully. The food you eat arrives in your stomach as organized molecules, complex carbohydrates, proteins, and fats that plants and animals assembled using energy from their own environments. Your body breaks these organized structures apart, extracting the energy stored in their chemical bonds and using it to maintain your own patterns of biological organization. The waste products you eliminate carry away the disordered remnants of this process. Carbon dioxide leaves your lungs, water and other wastes exit through your kidneys, and heat radiates from your skin into the surrounding air. These dispersed byproducts represent the scattered disorder that your body creates while maintaining its internal organization. Your circulatory system acts like a vast transportation network, carrying organized nutrients to every part of your body while removing the disordered waste products of cellular metabolism. Your heart pumps blood through thousands of miles of blood vessels, ensuring that every cell receives the materials it needs to maintain its complex molecular arrangements. This circulation requires constant energy input, contributing to the overall increase in universal entropy while sustaining the remarkable order of your living systems. Even your thoughts and consciousness emerge from this interplay between order and disorder. Your brain contains billions of neurons, each one a complex cell that maintains intricate patterns of electrical and chemical activity. These neurons communicate through carefully timed release of neurotransmitter molecules, creating networks of information flow that generate your perceptions, memories, and awareness. The organized patterns of neural activity that create your thoughts require enormous amounts of energy to sustain. Your brain, though it represents only about 2% of your body weight, consumes roughly 20% of all the energy your body produces. This energy powers the molecular processes that maintain the complex organization necessary for consciousness, memory, and thought. Yet consciousness itself seems to create new forms of order that extend beyond the biological boundaries of individual organisms. Through language, art, science, and culture, conscious beings like you organize information and ideas in ways that can be transmitted across space and time. The words you read, the concepts you understand, and the knowledge you accumulate represent patterns of organized information that persist beyond the lifespans of individual minds. This transmission of organized information creates what some scientists call cultural evolution, a process that operates alongside biological evolution to create increasingly complex patterns of order. Human societies develop technologies, institutions, and knowledge systems that maintain themselves across generations, creating forms of organization that span much longer time scales than individual human lives. Plants around you demonstrate another elegant approach to creating temporary order from universal disorder. Through photosynthesis, they capture scattered photons from sunlight and organize this energy into the chemical bonds of glucose and other organic molecules. Green leaves are molecular factories that reverse the normal flow of energy dispersion, concentrating diffuse light energy into organized chemical structures. But plants, like all living systems, can only maintain this local decrease in entropy by contributing to greater disorder elsewhere. They release oxygen as a waste product, emit heat during their metabolic processes, and eventually die and decompose, returning their organized matter to the cycles of decay and renewal that characterize all ecosystems. Ecosystems themselves represent larger-scale examples of temporary order emerging from and contributing to universal disorder. Forests, grasslands, coral reefs, and other biological communities maintain complex patterns of energy flow and material cycling that sustain remarkable diversity and organization over long periods of time. Yet these systems depend entirely on the constant input of solar energy and the continuous cycling of materials through processes of growth, death, and decay. The biosphere as a whole creates a thin shell of organized complexity around planet Earth, a delicate film of life that maintains itself by processing the energy flowing from the sun toward the cold depths of space. This global ecosystem represents perhaps the most complex example of temporary order that we know of in the universe, yet it operates according to the same fundamental principles that govern your individual cells. Life's ability to create islands of order within entropy's ocean depends on what scientists call dissipative structures. These are systems that maintain their organization by continuously processing energy and matter, taking in organized inputs and releasing disorganized outputs. Your body is a dissipative structure, as are all living organisms, ecosystems, and even some non-living systems like hurricanes and certain chemical reactions. Dissipative structures reveal something profound about the relationship between order and disorder in the universe. Rather than representing opposites that must fight against each other, organization and dispersion work together to create the dynamic patterns that make complexity and life possible. Order emerges from disorder and eventually returns to disorder, but in the process, it creates temporary patterns of remarkable beauty and intricacy. Your existence represents a brief flowering of organized complexity in the long history of cosmic evolution. The atoms that make up your body were forged in stellar furnaces billions of years ago, scattered through space by supernovae, gathered into planets by gravity, and organized into living patterns by the intricate processes of biological evolution. For a few decades, these atoms maintain the extraordinary arrangement that constitutes your life, your consciousness, your unique perspective on the universe. Eventually, the patterns that create your individual existence will dissolve back into the larger flows of matter and energy that characterize the universe. But the temporary order you represent contributes something irreplaceable to the cosmic story. Through your life, the universe becomes aware of itself, experiences beauty and wonder, and creates new forms of organized information that enrich the ongoing process of cosmic evolution. As you prepare for sleep, your body continues its quiet work of maintaining temporary order against the gentle pressure of entropy. Your cells repair themselves, your immune system patrols for threats, your brain consolidates memories and prepares for dreams. You are a living demonstration that the universe's tendency toward disorder does not prevent the emergence of extraordinary complexity and beauty. But what happens when we extend our view beyond the temporary patterns of individual lives to contemplate the ultimate fate of all organized structures in an expanding universe? Close your eyes and journey forward through time, far beyond your own lifetime, beyond the existence of our sun, beyond the formation of new stars, to a future so distant that the very concept of years becomes meaningless. In this far tomorrow, the universe has reached a state that scientists call maximum entropy, a condition of perfect equilibrium where all energy has spread as evenly as possible throughout all of space. This future universe bears little resemblance to the cosmos you see tonight through your window. The brilliant stars that now pierce the darkness have long since exhausted their nuclear fuel. The galaxies that spiral majestically through space have scattered their stellar contents across vast distances. The concentrated sources of energy that once powered stellar fusion, planetary formation, and the chemistry of life have dispersed into the most dilute form possible. Imagine this final state as a perfectly still lake on a windless morning. No currents disturb its surface. No temperature differences create circulation patterns. Every drop of water has reached the same temperature as every other drop. The lake has achieved perfect thermal equilibrium, a state where no further change is possible because there are no energy differences left to drive any processes. In this distant future, the universe resembles such a lake, but on an unimaginably vast scale. All matter has spread uniformly throughout space. All energy has diluted to the same low temperature everywhere. No heat flows from warmer regions to cooler regions because no temperature differences remain. The cosmic dance of energy transformation has come to rest in perfect, motionless equilibrium. The stars that shine above you tonight are temporary interruptions in this journey toward maximum entropy. Each star represents a concentrated reservoir of nuclear energy, burning hydrogen and heavier elements in fusion reactions that release tremendous amounts of light and heat. But even the most massive stars can only sustain these reactions for a finite time before exhausting their fuel and fading into darkness. Our own Sun, that reliable source of energy that has powered life on Earth for billions of years, will continue shining for another 5 billion years before beginning its final transformation. As its hydrogen fuel depletes, the Sun will expand into a red giant, eventually shedding its outer layers into space and leaving behind a slowly cooling white dwarf star. This white dwarf will radiate its remaining heat into the growing coldness of space for trillions of years, gradually approaching the same temperature as the cosmic background radiation that fills the universe. Other stars follow similar paths toward their final equilibrium with the expanding cosmos. Massive stars burn through their fuel more quickly, ending their lives in spectacular supernova explosions that scatter heavy elements throughout space. These explosions temporarily create new concentrations of energy and matter, seeding future star formation, but they also contribute to the overall dispersion of organized energy into scattered forms. Even the most exotic stellar remnants, neutron stars and black holes, eventually surrender their concentrated energy to the universal tendency toward equilibrium. Neutron stars spin down over cosmic time scales, radiating away their rotational energy as electromagnetic radiation. Black holes, those most extreme concentrations of matter and energy, slowly evaporate through a quantum process that releases their mass energy back into space over unimaginably long time periods. As this cosmic evening progresses, star formation gradually slows and eventually stops entirely. The gas and dust needed to create new stars becomes too dispersed to collapse under gravitational attraction. The universe enters what astronomers call the stelliferous era's end, a time when no new stars can form and existing stars continue their slow journey toward darkness. Planets, those complex worlds where chemistry and perhaps life can flourish, share the fate of their parent stars. As stellar energy sources fade, planetary surfaces cool toward the temperature of empty space. Atmospheres freeze and fall as snow. Oceans solidify into ice that gradually sublimes away into the vacuum. The intricate geological and atmospheric processes that make worlds like Earth possible come to an end as the energy sources that drive them are exhausted. Life itself, wherever it may exist in the universe, faces the same ultimate destiny. Living systems depend on energy gradients, differences in temperature or chemical concentration that can power the molecular processes necessary for growth, reproduction, and complexity. As these gradients flatten out in the approach to maximum entropy, the energy sources that sustain life gradually disappear. Yet even in this seemingly bleak ultimate future, something beautiful and profound persists. The approach to maximum entropy is not a violent destruction but a gentle settling into the most stable and peaceful state possible. It represents the universe's natural rest state, the condition toward which all processes naturally evolve when left undisturbed. Think of maximum entropy as the universe's way of achieving perfect democracy among all particles and energy. No region of space enjoys more energy than any other. No concentration of matter claims privilege over its surroundings. All forces have balanced. All gradients have smoothed away. The cosmos has reached a state of absolute fairness and equilibrium. In this ultimate future, the universe still contains all the matter and energy it has ever possessed. Nothing has been lost or destroyed. The same atoms that once formed stars, planets, and perhaps living beings still exist, but they have achieved the most probable distribution possible given the available space and energy. Maximum entropy represents not the death of the universe but its most stable and sustainable configuration. This final state also preserves, in some sense, the memory of everything that came before. The patterns of matter distribution, though impossibly dispersed, still carry information about the cosmic history that led to this equilibrium. The universe in maximum entropy is like a vast library where all the books have been dissolved into individual letters and scattered randomly, but where the letters themselves persist as testimony to the stories they once told. Scientists call this ultimate future state the heat death of the universe, though it involves no actual death or destruction. Instead, it represents the final victory of equilibrium over change, of stability over transformation, of rest over motion. It is the cosmic equivalent of a peaceful sleep from which no awakening is possible because no energy differences remain to power any form of activity. But even this seemingly final destiny may not represent the absolute end of cosmic evolution. Some theories suggest that quantum fluctuations, the fundamental uncertainty that exists at the smallest scales of reality, might occasionally create tiny departures from perfect equilibrium. Over unimaginably vast time scales, these fluctuations might accumulate into larger deviations, potentially giving birth to new patterns of organization and complexity. Other theoretical possibilities include scenarios where the expansion of space itself eventually reverses, causing the universe to collapse back toward a state of concentrated energy, or where quantum tunneling events might spontaneously create new regions of spacetime with different physical properties. These speculative futures extend far beyond our current scientific understanding, but they suggest that even maximum entropy might not represent the ultimate final word in cosmic evolution. For now, though, the universe remains far from this equilibrium state. Stars continue to shine, planets orbit in stable patterns, and complex chemistry creates the conditions where life and consciousness can emerge and flourish. The journey toward maximum entropy occurs on time scales so vast that billions of generations of stars will live and die before the cosmos approaches its final equilibrium. As you rest tonight in your temporary island of organized complexity, you exist during one of the universe's most dynamic and creative periods. The cosmic story continues to unfold around you, writing new chapters of stellar birth and death, planetary formation and evolution, and perhaps the emergence of new forms of life and consciousness throughout the galaxy. But even in this distant future of perfect equilibrium, something remarkable will persist: the information patterns that encode the strange and beautiful fact that a universe governed by simple physical laws can give rise to complex structures capable of contemplating their own existence. In the vast darkness beyond your window, scattered throughout the galaxy, exist the most enigmatic objects in the known universe. Black holes represent places where matter has become so concentrated that space and time themselves bend into impossible shapes. These cosmic mysteries challenge everything we thought we understood about the relationship between order, disorder, and the fundamental nature of information itself. Imagine a star much more massive than our Sun, burning through its nuclear fuel at an incredible rate. For millions of years, this stellar giant maintains a delicate balance between the outward pressure of nuclear fusion and the inward pull of its own gravity. The star shines brilliantly, converting mass into energy and radiating that energy into space, following the same patterns of entropy increase that govern all energy transformations. But when the fuel finally runs out, this balance collapses catastrophically. With no outward pressure to resist gravity's pull, the star's core contracts violently. Matter compresses beyond anything found elsewhere in nature. Atoms collapse into neutrons, then neutrons themselves compress beyond their normal limits. The gravitational field becomes so intense that nothing, not even light itself, can escape from the region around this collapsed matter. This is how a black hole is born, not through destruction but through the ultimate victory of gravitational organization over all other forces. The scattered matter of a massive star becomes concentrated into a region of space so small and dense that it warps the very fabric of reality. Time slows down near the black hole's edge. Space curves back on itself. The normal rules of cause and effect bend into strange new forms. From the outside, a black hole appears as a sphere of perfect darkness surrounded by a boundary called the event horizon. This invisible boundary marks the point of no return, the distance from the black hole where the escape velocity equals the speed of light. Anything that crosses this boundary, whether matter, energy, or information, appears to be lost forever to the outside universe. But black holes are not simply cosmic vacuum cleaners that destroy everything they encounter. According to Einstein's equations, they are objects with specific properties that can be measured and described. A black hole has mass, which determines the strength of its gravitational field. It can also have electric charge and angular momentum if it rotates. These three properties completely define the black hole's interaction with the outside universe. Here begins one of the most beautiful and puzzling discoveries in modern physics. In the early 1970s, physicist Stephen Hawking made a startling calculation. He discovered that black holes, despite their name, actually emit radiation. This Hawking radiation arises from quantum effects near the event horizon, where the strange rules of quantum mechanics interact with the curved spacetime created by the black hole's gravity. The radiation emerges as pairs of particles that spontaneously appear and disappear throughout empty space due to quantum uncertainty. Near a black hole's event horizon, these particle pairs sometimes separate, with one particle falling into the black hole while the other escapes into space. The escaping particles carry away energy, causing the black hole to slowly shrink over time. This process creates a fascinating paradox that sits at the heart of our understanding of entropy and information. As the black hole evaporates through Hawking radiation, it gradually returns all of its mass energy to the surrounding universe. But the radiation appears to be completely random, carrying no information about the specific matter and energy that originally formed the black hole or fell into it over its lifetime. Think of this like a cosmic shredder that can destroy not just physical objects but the very information about what those objects were. If you threw a book into a black hole, the book's matter would eventually return to the universe as Hawking radiation, but all information about the words in the book, the patterns of ink on paper, the knowledge it contained, would seem to be lost forever. This apparent destruction of information creates what physicists call the information paradox. According to quantum mechanics, information cannot be destroyed, only transformed from one form to another. When you burn a book, the information about its content still exists in principle, encoded in the positions and motions of all the smoke particles, ash residue, and heat radiation produced by the fire. But black holes seem to violate this fundamental principle by destroying information completely. The paradox becomes even more puzzling when you consider black holes from the perspective of someone falling toward the event horizon. According to Einstein's relativity, a person crossing the event horizon would experience nothing unusual at that moment. They would continue falling toward the black hole's center, carrying with them all their information, memories, and physical patterns until they reach the singularity at the black hole's core. But observers watching from outside would see something completely different. As the falling person approaches the event horizon, time dilation effects would make them appear to slow down and fade away, their information seemingly stretched across the black hole's surface forever. This creates two contradictory descriptions of the same event, neither of which fully resolves the mystery of what happens to information. Recent theoretical work suggests that the resolution to this paradox may require us to completely reconsider our understanding of how information and entropy work in extreme gravitational environments. Some scientists propose that the event horizon itself might not be the simple boundary it appears to be, but rather a complex interface where information becomes encoded in ways we don't yet understand. Other theories suggest that black holes might be connected to other regions of spacetime through wormholes, allowing information to escape through alternate pathways. Still others propose that the interior of a black hole might not exist in the way we normally think about space and time, with the black hole's entropy somehow encoded entirely on its two-dimensional surface. These ideas challenge our basic concepts of space, time, and information. They suggest that entropy and the flow of information through the universe might operate according to principles we have not yet discovered. Black holes become laboratories where the fundamental rules of reality reveal their deepest secrets and most profound mysteries. The entropy of a black hole, unlike that of ordinary matter, appears to be proportional to the area of its event horizon rather than the volume of space it occupies. This relationship, known as the holographic principle, suggests that all the information contained within a three-dimensional region might actually be encoded on its two-dimensional boundary, like a cosmic hologram. If this principle applies generally throughout the universe, it would mean that the three-dimensional reality you experience might actually be a projection from information encoded on distant boundaries. Your thoughts, memories, and the very atoms of your body might be manifestations of patterns stored on surfaces unimaginably far away. This possibility transforms our understanding of entropy from a simple measure of disorder to something far more fundamental. Entropy might represent the capacity of space itself to store and process information. The universe's journey from low entropy to high entropy might actually be a cosmic computation, processing the information patterns that give rise to stars, planets, life, and consciousness. Black holes also raise profound questions about the nature of time and causality. Near the event horizon, the normal flow of time becomes distorted. Events that take finite time for a falling observer might appear to take infinite time for distant observers. The usual relationship between cause and effect becomes ambiguous when information can become trapped at boundaries where time itself behaves strangely. These temporal effects connect black hole physics to the arrow of time that governs all thermodynamic processes. The irreversible increase of entropy that makes ice melt and perfume spread through air might be intimately connected to the irreversible capture of information by black holes. Both processes seem to define preferred directions in time, but their relationship remains one of physics' deepest unsolved puzzles. As you contemplate these cosmic mysteries from the comfort of your bed, you participate in one of science's most remarkable adventures. The human mind, a temporary pattern of organized information in an entropy-increasing universe, reaches out to comprehend objects so extreme that they challenge the very concepts of space, time, and information that make comprehension possible. Black holes remind us that the universe contains mysteries that push the boundaries of human understanding. They represent frontiers where our current theories break down and new principles wait to be discovered. In studying these objects, we probe not just the nature of gravity and space-time, but the fundamental relationship between mind and cosmos, between the patterns that constitute consciousness and the physical laws that govern reality. Yet even these extreme objects obey deeper patterns that connect them to the quantum realm where probability and certainty dance together in ways that defy ordinary intuition. Journey with me now into the deepest foundations of reality, to a realm so small that ordinary concepts of position, motion, and certainty dissolve into something far stranger and more beautiful. In the quantum world that underlies everything you touch, see, and are, individual particles exist not as solid objects with definite properties, but as clouds of possibility that somehow give rise to the predictable, ordered universe you experience every day. Every atom in your body, every photon of light in your room, every molecule in the air you breathe exists in this strange quantum state. An electron orbiting an atomic nucleus does not follow a specific path like a planet around the sun. Instead, it exists in a cloud of probability, simultaneously occupying all possible positions around the nucleus until the moment when something measures or observes its location. This fundamental uncertainty is not a limitation of our measuring instruments or a gap in our knowledge. It represents the actual nature of reality at its smallest scales. The electron genuinely exists in multiple states at once, in what physicists call a superposition. Only when the outside world interacts with the electron does it choose a specific position, velocity, or energy state from among all its possibilities. Think of quantum uncertainty like a coin spinning in the air. While the coin spins, it is neither heads nor tails but exists in a superposition of both possibilities. Only when it lands and you observe it does the coin take on a definite state. But unlike a spinning coin, which has a hidden definite orientation at every moment, quantum particles genuinely exist in multiple states simultaneously until observation forces them to choose. This strange behavior creates what seems like a fundamental conflict with the orderly universe of thermodynamics and entropy that we have been exploring. How can the predictable flow of heat from warm objects to cool objects emerge from a microscopic world where individual particles refuse to have definite properties? How can the certain increase of entropy arise from the uncertain behavior of quantum particles? The answer lies in one of nature's most profound principles, the law of large numbers. While individual quantum particles behave unpredictably, collections of many particles exhibit remarkably predictable statistical patterns. Flip a quantum coin once, and the result is genuinely random. Flip a trillion quantum coins, and approximately half will be heads and half will be tails, with a predictability that approaches certainty. The ice cube melting in your palm contains approximately 10 to the power of 23 water molecules. Each molecule exists in quantum superposition, with uncertain position and momentum. Yet the collective behavior of all these molecules follows the precise statistical laws that make thermodynamics possible. The uncertainty of individuals gives rise to the certainty of averages. This emergence of classical behavior from quantum foundations resembles the way a photograph emerges from countless individual dots of ink on paper. Each dot by itself reveals nothing about the overall image. But when millions of dots arrange themselves according to statistical patterns, a clear picture becomes visible. The quantum world provides the dots, and thermodynamics describes the pictures that emerge. Entropy itself gains new meaning in this quantum context. At the microscopic level, entropy measures not just the number of ways particles can be arranged, but the number of quantum states available to a system. Each possible arrangement of particle positions, energies, and quantum properties represents a different microstate. The second law of thermodynamics becomes a statement about the overwhelming probability that systems will evolve toward microstates that are more numerous than the ones they started from. The quantum nature of reality also helps explain why the arrow of time exists. In the quantum world, processes that appear reversible when viewed classically become fundamentally irreversible due to the loss of quantum information. When quantum systems interact with their environments, their delicate superposition states collapse into definite outcomes. This collapse process cannot be reversed, creating an inherent direction to time at the most fundamental level. Consider the light from your bedside lamp. Each photon began its existence in a quantum superposition within the lamp's filament, existing in multiple energy states simultaneously. When the photon finally escapes the lamp and travels toward your eye, it maintains its quantum nature, existing as a wave of possibilities spread throughout space. Only when it strikes your retina does the photon collapse into a definite interaction, transferring its energy to specific molecules in your eye. This quantum collapse happens billions of times per second in your visual system, each event irreversibly converting quantum possibilities into classical information. The photons that create your perception of the room around you represent the transformation of quantum uncertainty into the classical certainty of conscious experience. Your brain itself operates at the boundary between quantum and classical physics. While the neural networks that create your thoughts and memories function according to classical electrical and chemical processes, these processes depend on quantum mechanical interactions at the molecular level. The proteins that regulate neural communication, the ion channels that generate electrical signals, and the chemical bonds that store neurotransmitters all rely on quantum effects for their precise functioning. Some scientists speculate that consciousness itself might emerge from quantum processes in the brain, though this remains highly controversial. Whether or not quantum mechanics directly creates consciousness, it certainly provides the foundation for the molecular processes that make awareness possible. Your thoughts tonight exist because quantum uncertainty at the atomic level gives rise to the classical certainty of neural activity. The relationship between quantum uncertainty and thermodynamic certainty extends throughout the universe. Stars shine because quantum tunneling allows nuclear fusion to occur at temperatures lower than classical physics would predict. The uncertainty principle permits atomic nuclei to overcome the electrical forces that would otherwise keep them apart, enabling the fusion reactions that power stellar light. Even the expansion of the universe itself may have quantum origins. According to current theories, the initial conditions that led to cosmic expansion arose from quantum fluctuations in the very early universe. These microscopic uncertainties, amplified by cosmic inflation, became the large-scale variations in matter density that eventually formed galaxies, stars, and planets. The cosmic microwave background radiation that fills all space preserves evidence of these primordial quantum fluctuations. The tiny temperature variations that satellites detect in this ancient light represent the quantum uncertainty of the early universe, stretched by expansion to cosmic scales and frozen into the structure of spacetime itself. This deep connection between quantum mechanics and cosmology suggests that uncertainty and certainty are not opposing forces but complementary aspects of a unified reality. The quantum world provides the creative randomness that prevents the universe from becoming trapped in perfect, unchanging order. Classical physics provides the statistical frameworks that allow complex structures to emerge and persist within this quantum foundation. As you prepare for sleep tonight, your body demonstrates this beautiful partnership between uncertainty and certainty. The quantum processes in your cells create the molecular randomness necessary for the chemical reactions of life. Your DNA replicates itself using quantum tunneling effects that occasionally introduce random changes, providing the variability that makes evolution possible. Yet these same random processes, when integrated across billions of cellular events, create the remarkably stable and predictable biological systems that maintain your life. Your dreams, when they come, may represent another manifestation of this quantum classical boundary. The random activation of neural networks during sleep creates the unpredictable narratives of dream experiences. Yet these random events occur within the structured patterns of brain activity that neuroscience can measure and partially predict. The gentle transition from waking consciousness to sleep parallels the transition from classical to quantum descriptions of reality. As your awareness fades, the definite thoughts and perceptions of waking life dissolve into the probabilistic landscapes of dreams and unconscious neural activity. You cross a threshold where certainty gives way to possibility, where the classical world of definite experiences merges with something more fluid and uncertain. In this daily journey from waking to sleeping, you recapitulate the cosmic story we have been exploring together. Order and disorder, certainty and uncertainty, the individual and the collective, all find their balance in the gentle rhythms that carry you toward rest. As you settle into the gentle embrace of approaching sleep, your body and mind participate in the same fundamental process that governs everything from melting ice cubes to the expansion of the cosmos. The transition from waking consciousness to sleep represents entropy in its most personal and beautiful form, the transformation of organized daily experiences into the scattered possibilities that become tomorrow's insights and growth. Throughout this evening's journey, we have explored how the universe tends towards states of greater possibility, greater freedom for its particles and energy to explore new arrangements. Now, as your thoughts begin to soften and your breathing deepens, you experience this cosmic principle in the most intimate way possible. The structured thoughts and focused attention of your waking day gradually dissolve into the fluid, associative landscapes of dreams and rest. Your brain demonstrates entropy's creative power as it processes the day's experiences during sleep. The neural pathways that fired in specific patterns during your waking hours now reorganize themselves, forming new connections and strengthening useful associations while allowing less important details to fade. This nocturnal reorganization follows the same statistical principles that govern all entropy increases, transforming the ordered information of conscious experience into the more scattered but ultimately more flexible arrangements of memory and understanding. Sleep itself represents a beautiful example of how entropy creates rather than destroys. The organized vigilance of waking consciousness gives way to the dispersed awareness of dreams, where your mind can explore combinations of ideas and memories that would never occur during focused thought. In this state of decreased mental organization, new patterns emerge, unexpected connections form, and creative insights arise from the gentle mixing of previously separate experiences. The physical relaxation that accompanies sleep follows the same entropic principles. The tension held in your muscles throughout the day releases as organized stress patterns dissolve into random molecular motion. Your heart rate slows, your breathing becomes regular, and your body temperature drops slightly as your metabolic processes shift into the restorative modes that repair and renew your biological systems. Even this repair work demonstrates entropy's constructive nature. The cellular damage accumulated during your active day gets replaced not by returning to some previous perfect state, but by building new structures that incorporate the lessons learned from wear and use. Your body becomes slightly different each night as it rebuilds itself, adapting to the experiences of the day and preparing for the challenges of tomorrow. This nightly renewal connects your personal experience to the larger cycles of change that characterize all complex systems. Just as ecosystems renew themselves through seasons of growth and decay, just as stars rejuvenate the universe by transforming simple elements into complex ones, your sleep cycle participates in the cosmic rhythm of breakdown and reconstruction that allows complexity to persist in an entropy-increasing universe. The dreams that will soon visit you represent perhaps the most beautiful expression of entropy's creative potential. In dreams, the organized logic of waking thought dissolves into a more fluid form of mental activity where past and present intermingle, where cause and effect become negotiable, where the impossible becomes routine. This apparent chaos serves a profound purpose, allowing your mind to explore new combinations of ideas and emotions without the constraints of logical consistency. Dream narratives emerge from the statistical interactions of randomly activated neural networks, yet they often carry surprising wisdom and insight. Like the complex patterns that arise when you scatter seeds on fertile ground, the scattered activations of dreaming consciousness can grow into meaningful realizations that would never develop under the organized constraints of directed thinking. Your personal experience of entropy during sleep mirrors the universe's own creative processes on the grandest scales. Just as cosmic expansion has allowed simple hydrogen and helium to evolve into the complex chemistry that makes life possible, your nightly dissolution of organized consciousness allows simple sensory experiences to evolve into sophisticated understanding and wisdom. The relaxation flowing through your body right now participates in the same energy dispersion processes that govern stellar evolution and climate systems. The heat radiating from your skin joins the global circulation of thermal energy that connects you to every other living being and to the cosmic background radiation that fills all space. Your individual warmth becomes part of the universe's patient journey toward thermal equilibrium. Yet this joining with cosmic processes does not diminish your individuality. Instead, it reveals how your unique patterns of organization contribute to the universe's ongoing exploration of what is possible. Every thought you think, every experience you have, every dream you dream adds new information to the cosmic story, creating arrangements of matter and energy that have never existed before and will never exist again in exactly the same form. The entropy increase that governs your transition to sleep is not a loss or a failure but a transformation that opens new possibilities. The scattered neural activity of your resting brain will consolidate today's experiences into tomorrow's memories. The relaxed state of your body will allow healing and growth processes to unfold. The dreams that emerge from your unconscious mind will weave new connections between ideas and experiences that seemed unrelated during your waking hours. This creative aspect of entropy extends far beyond your individual sleep cycle. Throughout the universe, the tendency toward increased disorder creates the conditions that allow new forms of order to emerge. Stellar explosions scatter heavy elements that become the building blocks of planets and life. Planetary atmospheres mix and circulate, creating weather patterns that distribute energy and materials around the globe. Ecological systems cycle nutrients and energy through complex networks that sustain incredible diversity and beauty. Human culture itself demonstrates entropy's creative power. Ideas spread and mix across social networks, creating new combinations of knowledge and understanding. Languages evolve and change, developing new vocabularies and expressions that capture previously unexpressed thoughts and feelings. Art and music explore new combinations of colors, sounds, and meanings, expanding the universe's repertoire of aesthetic possibilities. Even science, our systematic attempt to understand the universe's patterns, progresses through entropic processes. New discoveries emerge when previously separate fields of knowledge interact and combine. Breakthroughs often occur when rigid theoretical frameworks relax enough to accommodate new observations and ideas. The growth of human understanding follows the same pattern of creative disorder that governs all complex adaptive systems. As you drift toward sleep, you participate in this cosmic creativity. Your relaxing awareness joins the universe's exploration of new states and possibilities. The dreams awaiting you will add new chapters to the ongoing story of how organized matter can become conscious of itself and contemplate its own existence within the vast, evolving cosmos. The beauty of inevitable change lies not in any final destination but in the endless creativity of the journey itself. Entropy does not drive the universe toward a static endpoint but toward an ever-expanding exploration of what arrangements of matter and energy are possible. Each moment brings new configurations that have never existed before, new combinations of particles and forces that express previously unrealized aspects of cosmic potential. Tonight, as entropy flows gently through your dreams and rest, you embody this cosmic creativity. Your sleep is not a withdrawal from the universe but a deeper participation in its ongoing becoming. The scattered thoughts of your dreaming mind, the relaxed circulation of your blood, the gentle rhythms of your breathing all contribute to the universe's patient exploration of its own infinite possibilities. In accepting sleep's approach, you align yourself with the fundamental rhythms that govern everything from quantum fluctuations to galactic evolution. You become part of the gentle, inexorable flow that transforms today's experiences into tomorrow's potential, that converts the organized patterns of waking life into the scattered seeds of future growth and understanding. Rest now in the knowledge that your sleep serves the same creative purpose as the expansion of space, the scattering of starlight, and the patient mixing of ideas across the networks of human culture. In letting go of today's organized thoughts and experiences, you open yourself to tomorrow's new possibilities, trusting in entropy's ancient wisdom that transformation, not preservation, is the path to continued growth and beauty.